When scaling prime number sieves in high-performance computing, mathematical efficiency eventually hits the hard limit of memory latency. The bottleneck is no longer the calculation, but the time required to move data from RAM into the processor's registers. In 2020, researcher Satish Kumar Singh introduced a potential solution to this architectural wall, the VMF-Segmented Sieve algorithm. Benchmark data reveals a significant performance jump. Compared to standard segmented sieves, VMF operates 5.8 times faster. This speed comes with a massive reduction in hardware footprint. The system requires approximately 83. VMF is built specifically to align with the pathways of 64-bit architecture rather than relying on new mathematical proofs. To achieve a 5.8x speedup, the algorithm treats prime sieving as a memory bandwidth problem rather than a purely theoretical one. Traditional sieving methods are computationally expensive at the instruction level. They rely on modulo arithmetic and division to identify and discard non-prime integers. These operations are notorious for stalling a modern CPU pipeline. They create frequent logical branches, and when the processor mispredicts those branches, it has to flush its entire execution queue and restart. The operational cost column in this complexity table highlights the issue. The sieve of Atkin relies on quadratic forms, while the classic sieve of Eratosthenes is burdened by continuous modulo and division logic. The VMF gap jump row shows the alternative. It eliminates complex logic gates entirely, replacing them with pure addition. This achieves a zero-branch execution state. The CPU pipeline never has to guess a logical path, staying fully saturated with data. Replicating this efficiency requires a three-part architectural strategy: primordial mapping, the rhythm table, and symmetrical execution. Zero-branch execution is only possible if the numbers are mapped into memory in a way that the hardware can consume linearly, without decision-making pauses. Standard sieves utilize a linear bit array, where each bit represents a single integer. If you were summing up to 1 billion, you begin with an array of 1 billion bits. VMF initializes differently. It establishes a base primordial, P19, which is the product of the first 8 prime numbers. Multiplying 2, 3, 5, 7, 11, 13, 17, and 19 together results in a value of exactly 9,699,690. VMF maps array indices strictly to the residues of P19. Multiples of the first 8 primes are never mapped to the array in the first place, leaving only the coprime candidates. This acts as a hardware-level pre-filter. By the time software begins, 83% of non-prime numbers have already been discarded from memory. The complexity table quantifies this reduction. The effective input size n is reduced to approximately 0.171 n. For the processor's arithmetic logic unit, this represents a massive reduction in raw workload. It only has to process 17% of the standard numbers. Treating each segment as a pre-filtered VMF block provides the foundation for the algorithm's massive spatial compression and high-speed execution. Because the multiples of the first 8 primes are missing from the array, the gaps between the remaining candidate numbers are no longer uniform. Navigating irregular gaps normally requires division or modulo logic to find candidates, triggering the pipeline stalls the algorithm is designed to avoid. VMF circumvents this by pre-calculating the Euler totient for P19. This identifies every possible gap between valid candidates before the sieving begins. These 1,658,880 pre-calculated gaps are stored in a 64-bit circular buffer, known as the rhythm table. During the execution phase, the system never calculates a distance. It simply streams the next jump value from the rhythm table directly into the ALU pipeline. The ALU performs a simple addition of this gap value to its current position, instantly finding the next prime candidate. This mechanism allows the pure addition highlighted in benchmarks. The heavy logic of a standard sieve is entirely replaced by a fast lookup table. The rhythm table trades memory storage for CPU cycles, turning an algorithmic bottleneck into an operation limited only by memory bandwidth. This mapping strategy directly dictates how the algorithm interacts with the CPU's internal memory. According to the space complexity table, while a classic sieve requires 1 bit per integer, VMF's residue mapping reduces this to 0.17 bits. This creates natural bit packing. Because the array only stores residues, the representation of the number line is significantly denser than a standard bit array. This density allows a 1 megabyte segment of memory to hold the equivalent of a 5.8 megabyte number line. When a segment is small enough to fit inside the processor's L1 or L2 cache, the CPU can access that data instantly. If the segment is too large, the CPU stalls while waiting for data to arrive from the slower main RAM. Because VMF's 0.17-bit density is so high, it can fit much larger ranges of the number line into these fast caches simultaneously, preventing the memory latency stalls that slow down traditional sieves. The 5.8x speedup isn't just about faster addition. It's the result of keeping the processor constantly supplied with data from its own local cache. The final stage is the jump strike, marking and removing composite numbers. The formula uses the seed prime and residue to calculate exact strike-off positions. Most sieves scan an array linearly, working from the first index to the last. VMF uses a different execution topology based on the primordial wheel's symmetry. This is known as mirror execution. Because the residues of a primordial wheel are symmetrical, every strike-off position has a corresponding mirror position. The symmetrical ALU processes these pairs at opposite ends of the segment simultaneously. The pointers move inward from the edges towards the center, striking off composite numbers in a single rhythmic pass. This bilateral processing is unique to primordial mapping and cannot be replicated in standard linear sieves like Atkin or Pritchard. By utilizing the primordial's inherent symmetry, the ALU calculates strike-off positions for two composite numbers at once, using the same residue offset logic. By processing these mirrored pairs in a single pass, the algorithm extracts twice the throughput from the execution unit without the overhead of multi-threading or inter-core communication. The VMF architecture succeeds because it treats prime sieving as a hardware synchronization challenge. Each component is designed to keep the 64-bit pipeline saturated. The technical summary reinforces these advantages. First, hardware-level filtering removes 83% of the workload before the ALU begins. Second, symmetrical mirroring doubles ALU throughput per clock cycle. Third, extreme bit packing density ensures the processor never waits for main RAM, eliminating latency stalls. This 0.17 bit per number density makes the algorithm highly effective for massive number theory computations that would otherwise exceed the RAM limits of modern servers. The research highlights a specific practical application for this high-speed, high-density processing, the massive data throughput requirements of 6G signal processing. Ultimately, VMF proves that at extreme scale, theoretical algorithmic complexity matters less than structural alignment with bare metal 64-bit architecture.